In the two previous videos, we saw the intuition and the proof for the ratio test. Now let's tackle the somewhat easier root test. The high school calculus version of the root test says that you can start with any series, take the nth root of the absolute value of the nth term, and take the limit as n goes to infinity. If that limit exists and is strictly less than 1, then the original series converges. If it's strictly greater than 1, then it diverges. The key to understanding the proof of the ratio test was the insight that if our limit is less than 1, then the series is eventually dominated by a geometric series of the form a times r squared, etc. For the root test, we'll see that if our limit is less than 1, then our series is dominated by an even simpler geometric series, one given by r squared, r cubed, and so on. So let's say that the value of our limit is 0.6. We can pick epsilon to be 0.2, and that means that from some point forward, the nth roots of the absolute value of the a sub n's will all be between 0.4 and 0.8. Great. Just raise both sides to the nth power, and we see that our series is dominated by the series 0.8, 0.8 squared, 0.8 cubed, and so on. And that's a convergent geometric series. That's the intuition. Now let's write out a proof. We will let big L be the limit of the nth root of the absolute value of the nth term, and we will assume that big L is less than 1. Similar to our ratio test proof, we can pick epsilon to be half the distance from L to 1. This guarantees that L plus epsilon is still less than 1. The definition of a limit says that there is a big N, so that all the terms past the big nth term have an nth root less than big L plus epsilon, which we made sure was less than 1. So the absolute value of a sub big N raised to the 1 over big N is less than L plus epsilon, and the absolute value of a sub big N plus 1 raised to the 1 over big N plus 1 is less than L plus epsilon, and so on for all the subsequent terms. Everything here is non-negative, so we can undo the radicals. Just take the first inequality and raise both sides to the big nth power, take the second inequality and raise both sides to the big N plus first power, and so on. And magically, we see that our series, beginning with the big nth term, is dominated by the geometric series whose nth term is L plus epsilon to the nth power. Now we know that L plus epsilon is a positive number less than 1, so this geometric series is a convergent one. This tells us that our original series, starting with the big nth term, is convergent, so we can conclude that the entire series converges. Let's do the L greater than 1 case. Like with the ratio test, this case is not too tough. We can again pick epsilon to be half the distance from 1 to L, so we let epsilon equal the quantity L minus 1 all over 2. Since the nth root of the absolute value of a sub n approaches L, we know that from some point forward, that nth root will be within epsilon of L. So in the language of real analysis, there exists big N such that for all n greater than or equal to big N, L minus epsilon is less than the nth root of the absolute value of a sub n, which is less than L plus epsilon. We only care about the first half of that inequality, so let's rewrite that, and we will add in the fact that 1 is less than L minus epsilon. So for all n greater than or equal to big N, 1 is less than L minus epsilon, which is less than the nth root of the absolute value of a sub n. Everything here is positive, so let's raise all three sides to the nth power, and this shows us that for all n greater than or equal to big N, the absolute value of a sub n will always be bigger than 1. This means that the a sub n terms cannot possibly converge to 0, so once again, our series flunks the 0 test, and it therefore diverges. Now in both the proofs of the ratio test and the root test, you may have noticed that we kept throwing away half our inequalities, and that's a clue that our hypothesis was too restrictive. In other words, the theorems can be made stronger, and they can handle cases that your calculus teacher never told you about. More on that in the next video. Be sure to subscribe to get notified when it comes out, and by hitting the like button, you help us create more videos like this one. Finally, we do read the comments, so feel free to leave a note about how exhilarating this all was.